welcome to the lecture. Seems like there's more people here than usual. I'm curious about why that's the case, but anyway, so today is a bit unusual. We have a mix of different presenters. So first we will have Edja, who's one of the TAs, and he will present an Aikido tutorial, which I believe you'll need for your labs 3 and 4, not lab 2. And by the way, that was due, I think, yesterday or recently. So hopefully that went well, and there's not too many late days that you need to use. So and then after that, we will have Shivan give another presentation, I believe, on quality diversity algorithm. And then I will conclude with some midterm review questions. So yeah, any logistical questions? Well, so Hedja, you want to get started?
Okay. Okay, hello everyone. My name is He Jia, and I'm one of the TAs. So today I will first give you a tutorial on Aikido, which is a programming library that you will use to complete your lab homework. And then I will briefly talk about foundation models and its applications in robotics. So, okay. And Aikido stands for artificial intelligence for kinematics, dynamics, and optimization. So kinematics, dynamics, and optimizations are all, including artificial intelligence, are all important topics in robotics. And okay, and this is a programming library that is developed and maintained by several labs from different universities. And it is a collection of useful code for developing complex robotic systems. So it can be used to compute kinematics and dynamics and perform motion planning, those kind of things. And you can use it to model robots in simulator. So in this tutorial, I will first briefly go through how to set up the environment and how to run a simple demo with the Aikido. Okay, so I think this you can find it detailed instructions on Piazza, and so here I will just briefly go through. We will use virtual machine software, and I think you can download the virtual machine image from Piazza, which has included all the necessary files. And once you launch the VM, you will need to download the Catkin workspace. Catkin workspace is are some files for ROS development. And then you will to do your lab work, you will write some code, and once you finish the coding, you can build this build your code with some ROS commands. So, and here, so I'm not sure if you are familiar with ROS. Wait, do you have you had the ROS tutorials? Okay, so here I show some steps to run a simple demo that is developed based on Aikido. And you will have to run ROS code to launch the ROS master node, and you will use Avis to for visualization. And then you will use this setup.bash script to set up the environment variables. And then this simple trajectory stop high is a simple demo developed based on Aikido. And once you run this file, and in the Avis, you can add an interactive marker. Interactive marker is basically a ROS topic that listens to ROS it's something that listens to a ROS topic where we publish some visualization methods. And I have recorded a short video showing how to run this simple demo. So So you first use ROS core to launch the ROS master node, and then you launch up this. And then run the Python script, the demo script. Oh no, the setup the environment. There it goes. And I think for different environments, for some environments, you may need to use Python 3. But in my environment, I'm using Python 2.7. Huh? Okay, so here you can see how the robot moves. So you have to quickly add the interactive marker. Otherwise, it will, because the script will finish very soon. So you have to add the interactive marker and see the robot moves before the script finish running. Okay, so get close. Okay, so now I will briefly go through that demo script, and in our lab work we will all use Python to do programming, and we will use AdaPy. AdaPy is a Python wrapper of libada, and libada is a library depending on Aikido for using Jekyll arms. So this is the Jekyll arm, and we will also use it for our real robot experiment, real robot lab. And in the demo script, we first input AdaPy, and then we will use AdaPy.ada to instantiate a robot. And we can use these lines of code to add different objects into the world. So this can be useful when you want to add these obstacles. So you want to treat them as obstacles, and you want to plan some collision-free paths for robots. And then we can also add the self-collision checking with this function. So in libada or Aikido, there are two important concepts or important class. So one is a skeleton class and one is a state space. So in the skeleton class, it has all the kinematics and dynamics information, and this information includes robot joint positions and geometric shapes of the robot limbs. And the state space class contains information like how many joints the robot has and what kind of joint types. So you can use this get arm skeleton function and the get arm state space function to get the skeleton or state space of the robot. And then we will use compute joint space path function to plan a joint space path for the robot. And a joint space path is basically a sequence of sequence of waypoints, and each waypoint is a vector. So basically, each waypoint is a vector of the joint values. So the joint positions of each joint of the robot. No, of the. So there are also a lot of other useful functions you may use. I think you may use computer smooth joint space path, and you may use setup collision detection. These functions. So the first function is will be used to compute a smooth joint space path, and setup collision detection is used to set up collision constraints. So you can set up collision checking for robots and the environment objects, or robot and itself. And you can use plan to configuration function to plan a joint space path to reach a given joint path, joint configuration. So joint configuration is the positions of each joint of the robot. And when we do so once you get a trajectory from the plan to configuration function, or compute smooth joint space path function, we want to execute this trajectory. So we will use the execute trajectory function. And I think that these are basically all you need for your lab work. Okay, then now I will talk about a little bit about foundation models and its applications in robotics. So, traditional robots used to be limited to industrial environments, and basically these industrial robots are for like mass production industry. You want to you can use robots to assemble cars and those things. And the reason why they are limited to like mass production environments is because these environments are usually structured and static. So also the tasks are structured and static. So the tasks are fixed and repetitive. And in these environments and for these tasks, it's easy to program robots because robots are basically doing repetitive things, and you can just, for example, if you want a robot to bring you a part of the car, you can just define where the robot can pick up the part, and where it should deliver to. And usually in these environments, these pick and place positions are usually fixed. So it's very easy to program these robots. But nowadays, more and more people are trying to enable robots to be deployed into more diverse tasks and environments. For example, we want robots to be deployed into homes, human homes, or hospitals. So, usually these environments are dynamic and diverse. So this requires robots to be requires the robot to have more powerful capabilities, and we want them to be able to handle different tasks, different objects, and different humans, and different basically many different things. And machine learning has become one of the most powerful weapons towards this goal, because learning agents usually can handle noisy observations, complex dynamics, and complex human instructions. So, however, if we want to use machine learning, like a lot of work on robot learning tries to learn separate models for different tasks. And so if we want to enable robots to be deployed to a different task, we may have to learn a new model from scratch. And usually learning these new models requires collecting a lot of data, which is expensive, and also it can take time to train robots for new tasks. So we want to ask, like, can we learn a single model for various bodies, tasks, and environments? And the foundation models can be like one way to do that. Foundation models are models that are trained on large amounts of data. And these models can be applied to a wide range of downstream tasks. So once you trained a foundation model, usually it can be used in many different downstream tasks so because you can use sometimes you can just do zero-shot transfer, but sometimes you can also do in-context learning or fine-tuning. You can do different things to make it work for different downstream tasks. So now I will introduce three different foundation models. So the first one is for language tasks. So large language models is very popular recently, and one of the most well-known model is called known as GPT, and so it stands for Generative Pre-trained Transformers. And these kind of models use transformers as a neural network architecture, and so in its name it has a pre-trained. And so to do the pre-training, it can use different ways to do pre-training. So one way is so here I'm talking about the language tasks. So one way to do pre-training is to first give the model a sequence of words and ask the model to predict what word will come next. And another way to do pre-training is to give the model a sentence and ask the model to first encode it into a vector, and then ask it try to decode it back to the original sentence. So with this, after pre-training, the models can usually learn some general knowledge from the data set. And because this kind of pre-training can be unsupervised, so you can do this training on a very large scale of data set. But if you want, so after pre-training, we also want the models to be able to produce high quality answers. So for example, nowadays we are using ChatGPT and these things. These models can generate very high quality, like human-like output. And that's because after pre-training, they also do some supervised learning. So one way to do supervised, so here in chat, I got it from the ChatGPT website, and the first step is to collect some demonstration data, and this demonstration can be, for example, a pair of question and answer, and the answer is provided by some human labeler, and and with this kind of label data set, we can fine-tune the pre-trained model. And once we fine-tune the pre-trained model, we can also collect some comparison data and train a reward model. So basically, we will have some data labeler that ranks the outputs from the models. And with this, we can train a reward model that can be used to rank different outputs from the sample from the model. And with the reward model, we can do some reinforcement learning and to continuously improve the current model. So this is how they can get better and better output quality from the model. So the large language models is used to process language tasks, but we also want to, so for example, in robotics, we have different modalities. We have language, we have vision, and also robot actions. And the second kind of foundation models for connecting vision and language. So here I show a figure from a paper of an famous model called CLIP. So in the CLIP, we want to we also want to do some large scale pre-training, right? But we want to connect vision and language. But it's hard to, for example, if I want to do some supervised learning, it will be very expensive to collect very large scale data set. So we want to do some unsupervised learning. And in CLIP, the way to do pre-training is to collect some images together with their text descriptions. Because on the internet, we can very easily find images and their corresponding text descriptions. So with these pairs of text and images, we can learn text encoder. We can learn a text encoder model and an image encoder model, and we try to maximize, like the text encoder will encode the text description into a vector, and the image encoder will also encode images into a vector. And we want to maximize the cosine similarity of the encoded vectors of the paired image and text description. And we also simultaneously minimize the cosine similarities of the vectors or embeddings of not paired text and images. And then with this pre-training, the models have learned a lot of knowledge, general knowledge from the images and the text. And we can use these models for many different downstream tasks. So one example downstream task is like doing a label classification task. So for example, if you give me an image of a dog and you want the model to classify what animal it is, right? So you can first you can provide a set of options, animal options, and then you try to, if you fill this sentence with different options, and you try to compute the cosine similarities of the text embeddings and the image embeddings, you can select the most likely animal label as your output. So this is one way to, this is one example application of these models. Okay, but in robotics, we also our ultimate goal is to have robots generate actions. So we don't stay only on the like language tests or vision tests. We want to generate robot trajectories that can change environment states, change objects. So so this work RT2 is like the recent work from Google, and they want to like fine-tune some large language model, some large language vision models to include robot action data. But because in our in robotics, we usually represent robot trajectories as a sequence of numbers. So how can we connect this representation with like language tests and vision tests? So in their method, they try to tokenize the actions. So they represent actions as 3D translation of the robot and gripper, and also the rotation, like 3D rotation of the robot gripper. And with this, they kindly tokenize robot actions. So they can collect some robot action data set and use this to train or fine tune the large language models. No, vision language models. And they call it vision language action models. And they do not just fine tune, like they do not fine tune a pre-trained models with robot action dataset, but they merge the language task dataset, vision task dataset together with the robot action dataset and do some fine tuning. It's not just like you have a robot action data and you only fine tune the models on the robot action data. So I think that is an important detail. So recently we are me and Professor Daniel Sita and some of my lab mates trying to use large language models on lower level robot manipulation tasks. So we are focused on fabric manipulation tasks, and we focus on fabric smoothing task and fabric folding task. So this is roughly a architecture of our method. So given an image and some descriptions of the smoothing task or folding task, we want to see if ChatGPT has this knowledge to tell us which point should we pick, should the robot pick on the fabric, and in which direction to point, or in which point to place it, so the robot can finish a smoothing task or a folding task. And I can show you like a current result from our method. Oh, wait. It's a GIF. Oh, sorry. Oh, so you can see how so at each step our method will input an image of the observation of the fabric and the target of the smoothing into ChatGPT and ask ChatGPT to give some good pick and place points to do a smoothing task. This shows kindly ChatGPT has some general knowledge of doing this kind of tasks. So I think this concludes my presentation. Happy to answer any questions.
Question. So the paper that is on that slide is due at the end of this week, so very cutting edge. Give us one. Oh yeah, one question.
Can you speak louder?
When you are feeding the model.
What?
When the paper is on the thought is stronger. So when you are feeding the model, how do you determine which act?
So you are saying, are you asking like how to decide which point to pick? So Can I talk about the details?
Wait, are you asking like where do we decide where to graph the fabric? That's GPT, ChatGPT tells us. Yeah, that's basically the whole point of it. And by the way, it's not trivial to get it working. Like if you magically provide the image to ChatGPT and ask where do you graph it, it doesn't work. Which that's a very interesting. So ChatGPT seems to suffer from a similar paradox that reasoning about stuff that seems simple, like grasping something or that right spot is difficult than generating complex code. So I find it very interesting. But anyway, I think we'll be able to talk more about this paper in week 1 3 or make it fun. Yeah, any other question before we move on to the next speaker?
Can you say again? Here, here.
BBC models have trouble certain problems. And traditionally that's not the problem with like recent questions, but in applications like this, it's that problem. You know what I'm saying? I don't know if you know.
Oh, yeah. Yeah, I think, so you're asking, sometimes GPT will give some, directional answers and,
Yeah, you know the topic.
yes. So, but, so in robotics, we usually, like, if you give me so first of all, we have simulators and then we can, before execution, we can kindly validate whether these actions are safe or like, good. So I think we can, before really executing what GPT suggests, we can do some validation in this to ensure safety. But that, yeah, I think, yeah, that's basic.
All right, let's move on to the next speaker. And yep, thank you, Dan.
Did Stefano tell you the news today? No. He has.
Jack, can you stop sharing? I think if you are, I think only one person can share the time.
I should mute too. Sure.
It's Hey, sorry, Daniel, am I supposed to do anything else after I'm sharing? It's not showing up.
You have one unit.
Oh. Finally.
I didn't go on because I can see your.
Okay, yeah, so I thought that was hooked to the Zoom as well. So anyways, hi folks, my name is Shehan and I'm a first year PhD student from the Icarus lab. And our lab does a lot of work on policy diversity algorithms, or QD. So I thought today I would give a short overview on QD algorithms.
Can you move the image here?
Oh, yes, my apologies. Yeah, like that. Okay. And I'll try to focus more on how to use quality diversity algorithm to generate diverse set of control policies, because after all, this is a robotics class. So as the name suggests, quality diversity algorithms simultaneously try to optimize for two things, quality and diversity. The quality bit should be fairly easy to understand because, well, we're trying to obtain a policy and we want it to be good. So for example, if we're trying to control a bipedal robot to move forward, then hopefully we want it to move forward as quickly as possible. So good behavior, that's nothing new. But what might be less intuitive though is why we also want a diverse policies. That corresponds to the second thing that QD quality diversity algorithms are trying to optimize. So instead of a single good policy, QD algorithm try to obtain a diverse set of policies, each of which behaving in a slightly different way and each of which being locally the best in terms of performance. So I thought before we start talking about QD algorithms proper, we should review like some of the advantages of having a diverse set of policies instead of a single one. So the first advantage of having a diverse set of policies is that those policies in the set can be used as backup policies in case of some sort of failure. So for example, you might have a very good policy, but then something changes about the environment, or maybe for a more concrete example, your robot gets damaged. Then you want to still have a policy to switch back into. And if you have a diverse set of policies, then you can just simply fall back to one of those policies. And that is probably often preferable to, for example, learning another new policy from the ground up, but that argument might be somewhat weakened in recent years because of all the advances in zero-shot learning. But anyways, here to the right, this picture shows a puppy who unfortunately lost a leg, but he was nevertheless able to adapt and recover running skill by switching from a 4-legged gait to a 3-legged gait. So the second advantage of having a diverse set of solutions, policies, is that you can show these policies to the user. This is especially useful in a human-robotic interaction setting because, well, the human user might have some sort of preference regarding how they want their robotic partners to behave. And it might be difficult to put it into words. And even if they could put it into words, it's often difficult to parse it into meaningful information. But what is easier for them to do though is to pick one that they prefer. So if in this case, if I show the user these 4 policies for controlling the bipedal walker to move forward, maybe the user just doesn't know like how they want the arm joint angles to bend and etc. But they can say, okay, I really like this this one, which is kind of doing like a Naruto run. So I'll just pick that one. And then some downstream things such as contrastive learning can take advantage of that information. Okay, the third advantage, well, this originates from a problem in reinforcement learning called the exploration-exploitation trade-off. I think you're going to learn about it later in this class. So essentially, when we're trying to search for a policy, we might get stuck in some local optima, which is optimum, which is better than its surroundings, but it's not like the globally best solution. And we may lose further motivation to improve it any further. That would be a problem when we are trying to optimize a single solution, so a single policy. But if we have a diverse set of policies and we're trying to optimize all of them, then the likelihood is that some of those diverse policies are going to land in a better place than the local optimum that we would have otherwise landed in. So that is another advantage. And the fourth advantage is kind of a trivial one, like why not? If we're trying to optimize for a solution, then a policy, then there will be some like intermediate policies that we get halfway, which are not quite the best in terms of the objective as the truly optimal solution. But I mean, they might be optimal in some other regards, and we might just want to keep them and save them for like a just in case. And by doing that, we get all these aforementioned advantages, and the cost is trivial. So like, why not? Okay, so hopefully now that you're convinced that diversity is a good thing, we can begin talking about QD algorithm. And the first natural question is, how do we even define diversity? Maybe an intuitive first idea might be to just simply do something such as a parametric crowding distance. So in this case, say if we're trying to, say if we have a policy as a neural network, then we may compare two policies by comparing the weights and doing the like a Euclidean distance kind of thing between these two neural networks. And then essentially we can evaluate the diversity in the entire set by, for example, summing up the closest neighbor Euclidean distance for each solution, each policy within the set. But there is a problem with this approach though, and that is that the distance within the parameter space often does not translate well to distance within the behavior space. And it is the latter that we actually want. So I really like to use this example. It's called the competing convention problem. So in this case, essentially when we're trying to compare two neural networks and we compare them by computing the Euclidean distance, what we're essentially doing is that we're comparing each pair of these indices. But there is no guarantee that the same index means the same thing across two weight vectors. So by doing this Euclidean distance calculation, we're ignoring that. And yeah, for example, in this case, we might have two networks that have very large Euclidean distance in terms of weights, but they're essentially learning the same thing, except their subfunctions are somewhat swapped. Okay. So I guess the lesson that we can learn from that is that we really want to measure diversity by comparing the end behavior of our policies instead of the parameters for the policies. And because of the nature of this diversity, we often want this behavior that we want to compare to be defined by the user. So therefore, we have this thing called measures. These are user-defined end behavior features that we want to compare two policies based on. And so again, for example, if we're trying to compare to, so if we're trying to like generate policies that control a bipedal walker to move forward, then maybe alongside the objective, which defines like how fast the bipedal walker moves, we can have two measure functions, user-defined. One might be like the proportion of time the right foot touches the ground, and the other might be the proportion of time the left foot touches the ground. So say this is the right foot and this is the left foot. Then if we have a policy which essentially hops on the right foot, then maybe the right foot touches ground half the time while the left foot doesn't touch ground at all. So that would generate a policy which belongs to maybe something around here. And yeah, so essentially we have this grid cell, and we want to, we can define the diversity of our set of solutions by considering like how many of these cells are filled, because each of these cells defines a niche which satisfies a certain combination of measures. And also one thing to note is that it doesn't require the user to define a distance function. So the user would only need to come up with like two things we care about, and maybe also like how many cells we want to separate this measure over. So it's kind of convenient. Okay, so I guess that kind of justifies the diversity aspect of quality diversity. So overall, the quality diversity algorithm, again, attempts to find a diverse set of solutions each of which behaves in a slightly different way, but also is locally optimal within its niche. And in a high level, we can consider quality diversity as a problem of like trying to fill as many of these cells as possible with good solutions, of course. Okay. So now we're ready to talk about the QD algorithm in somewhat more concrete terms. And in general, QD algorithms can be thought of as consisted of three components: the archive, the emitter, and the scheduler. And now we're going to talk about each of them. So first of all, the archive. This is what we've been talking about, this grid-like kind of thing. Again, it is discretized or tessellated according to some measures which the users define. And essentially each cell defines a niche which satisfies certain combinational measures, and we want to fill as many of these as possible. But this doesn't have to be a grid. For example, there is this other kind of archive called CVT, which stands for, I think, centroidal Voronoi tessellation. It's kind of a fancy name, but I think that the general idea is that instead of having a bunch of cells, you have a bunch of centroids, and you define niches based on, like, given a solution, what is the closest centroid within this set. So we can have this alternative form of archive. There are also ongoing work about using generative models as archives, so it's not restricted to just a grid. The second component is the emitter. This is what we use to generate the candidate policies that we want to evaluate and potentially add to the archive. In a very simplest sense, this can just be a random sampler. So we can just sample within the parameter space and get a policy, and then we evaluate that and possibly add that to the archive. But of course, there can be more complicated emitters. For example, there can be like crossover or mutation from the evolutionary computation literature, or there can be CMAS, which stands for covariance matrix adaptation evolution strategy. So this is like a more informed version of emitter, which learns to actually produce more plausible solutions, which are more likely to be added according to past experience. But unfortunately, we don't have the time to talk about it in detail. And some of those emitters that we use to generate solutions, some of them might be good at generating diverse solutions, which means discovering new cells. Some of them might be better at improving existing cells. So maybe they already have a solution within the cell, and it's good at making this solution policy better. So we can have multiple such emitters to leverage the advantage of all of them. And which brings me to the third component of QD algorithm, the scheduler. So this is what we use to define the order by which we query the emitters. In a simple sense, this can just be round robin. So we can just go to each emitter like in a fair way and just query them one at a time. But again, there can be like more intelligent ways of doing this. We can use the bandit kind of scheduler, which again tries to learn to query the most promising emitter according to past experience. Okay, so now I thought I could present like a very simple QD algorithm called map elites. If we view this in the context of the three components that we just talked about, we can consider map elites as having the grid archive as the archive, the random sampling plus mutation as the emitter, and it only considers one emitter, so it doesn't have a scheduler. And the general workflow of map elites is that, well, it uses emitters to generate a bunch of candidate policies, and it evaluates them for their measures and also their objective scores. And then as it assigns the candidate solutions to their respective niches, cells, according to like their measure combinations. And if the cell is already occupied, then it compares the objective score of the new candidate solution against that of the existing old solution, and essentially replace the old solution if it's a better score. And if the cell is empty, then it just simply adds automatically. And also, well, I just said it always adds when the new solutions is better in objective, it's better in terms of objective than the old one, but it doesn't have to be the case. We can use some, apologies. We can use some sort of simulated annealing here. So maybe accept with some possibility, even a worse solution, just for the sake of making the search space smoother. Okay, and now here I list some of the QD algorithms. Here we have MapLease, and here we have some other improved versions of the algorithms. I don't have the time, unfortunately, to go over all of them, but here are the links, and you can check them out if you're interested. And I've also added this like one-line descriptions to like describe kind of what is the main innovation of these algorithms. So for example, the CVT MapLease uses the downward centroid Voronoi tessellation archive. And then we have CMA-ME, which uses CMA-ES estimator. But these are only meant to help you like organize the relationships among these QD algorithms, so they may be a bit on the overgeneralizing side. Okay, so yeah, now I'm going to show a few demo problems where we apply the QD algorithm to generate a diverse set of control policies. All of these are reinforcement learning domains, but we readapted them to QD setting by defining some measures. So for this first one, the Mojoko ant, this is a very popular RL domain. The objective in general is to control the kind of ant-like robot, four-legged, to move along the x-axis as quickly as possible. And the state we get here are things such as the center of mass of the robot, the joint angles, the lag contact states, etc. And action is just the new joint positions. And in this case, our user-defined measures, there are 4 of them, are the proportion of time each leg touches the ground. So you can think of it as like a kind of leg utilization defining feature. So if we have one leg always touching the ground, then it's probably an indication that we don't use this leg a lot. It's like just dragging behind. Yeah, so something like that. And this is the result we got after running CMA Mega, which is one of the more recent QD algorithms. I did this a few years back, so well, I didn't know how to put 6 GIFs together in a table form. So in my infinite wisdom, I just put them in a HTML. So the frame rate is kind of in the dumpster. But hopefully you can see like this one on the top left. This one is barely lifting the front right leg, whereas this one is like doing the lifting and it's using its front right leg more actively. And then the second demo problem that I'm going to present is the lunar lander, which is once again another popular RL domain. The objective is to essentially control a lunar lander to land within a certain landing region while saving energy, which means to move as gently as possible. And the state are the position, velocities, etc. of the lunar lander, and the actions are these discrete actions. And in this case, the 2 measures that we define are one, the touchdown x coordinate. So where is the x location where the lunar lander makes the first touchdown? And the other is the touchdown y velocity. So like how hard the lunar lander lands. Hopefully it will make more sense in the next slide. Okay, so pause. So here we actually show what the archive looks like. In this case, you can see, oh shit, I'll just pause. This here is the first of these 2 measures that we defined. This is the second measure. And the color within the heat map essentially shows like what is the objective score like within each of those combinations of measures. And for the first policy we're showing here, this one has a low touchdown velocity and a touchdown position all the way to the right. So you can see that is exactly what it does. Travels to the right, then gently touchdown, and then slides to the middle. Yeah, it's similar for the other one. So this one has, again, gentle touchdown, but it first touches down all the way to the left. And this is what it does. Gentle touchdown, slides into the go region. Okay. And then the final problem I'm going to present is the slime volleyball. This is probably less like well heard of, but essentially what you're trying to do here is to control an agent to play volleyball against an opponent. And the goal is obviously to have the ball land within the opponent's quarter. And again, the action is these discrete things. The state is the position of the agent you're controlling, as well as that of the opponent, as well as that of the ball. There are other states, but not going to include all of them. And the measures that we are defining here, according to our supposed like interest, how we want the agents to diversify, are one, the number of ball hits. So like how many times the ball bounces on the agent I'm controlling. And the second is the number of volleys. So like how many times the ball crosses the volley, the net in the middle. And again, here we show the archive. So this first one is supposed to have a large number of hits and also a large number of volleys. So as you can see, the way these two agents behave is that they try to stick close to the net, because just intuitively, this is the most straightforward way of getting more hits and more volleys, because the agent can just like do these small bounces. And then in a second example, policy, we have another policy which has fewer hits but more volleys. So in this case, the agents stay further away from the net and they try to bounce the ball as highly as possible to get fewer hits. But nevertheless, it crosses quite often. Yeah, so that's all I have to present. And yeah, just by the way, if you're interested, this seems like something you want to do, please check out PyRips. This is QD algorithm GitHub repository. It also includes some nice tutorials on QD. So yeah, I'm going to share the presentation slides to all of you after this, so you can have all this content. Yeah, I'll be. Thank you.
Question. Maybe you can play the volleyball video again while we wait.
Okay. Yeah, it's fun to watch.
I mean, not that, but the video with flying ball. Yeah, yeah. Ball.
Yeah, it's the same video.
I think video we can skip the
Oh, okay. Oh yeah, no, slide model. Sorry, the other one.
Have you played it?
Oh.
Say your objective is to use the least energy to move from one space to another, and you have a number of policies that can do that. Do all of them have the least energy, or is one of them the most efficient policy?
Sorry, can you specify what you mean by energy?
So your objective is to move from point A to point B using the least energy of the least time, right? Like one of your examples.
Yeah.
So do all of the policies have the same time and energy, or is there one policy that is most efficient?
Oh yeah, sorry. Maybe I didn't explain this quite clear. So the idea is, first of all, not all policies have the same energy, of course, but it's like we categorize the policies into this like individual niches, each of which satisfy a certain combination of measures. And within each niche contains a single policy which has locally the least energy, like within this niche. So I'm not sure if that makes sense.
All right, so there's no more questions, but maybe take a 4 or 5 minute break and then we'll move on to the midterm.
Stop sharing. Yes.
Sorry, I muted on Zoom, so yeah. I think, all right, so to recap, I think for people who are looking at the recording, I think we talked about midterm policy, then the question were like, basically everything that we have covered in class up to and including next Wednesday class is fair game, but we will be reasonable. I mean, if we talk about a research paper, I'm probably less likely to ask you the details of like a research paper and more likely to ask you like something more fundamental. And you don't have to like write in pseudocode or like no Python code for the exam. And then it's a mix of short answer computational question and then just question where you write a couple of sentences. Yeah, and again, we have some detailed instructions on the first page of the cover sheet, so I'm hoping it should be clear. Like, because I remember when I was a TA before, like we had a major complaint from students when some questions were not clear. So I tried to be unambiguous. So the question might be difficult, but at least it's unambiguous what we're asking. That's my intent. Yeah. But anyway, so yeah, sorry, I forgot to unmute myself, but we do optimize for the in-person class, so it's not like a professional recording here. Yeah. All right. Anyway, sorry. So actually, I should get my Google Doc open with the student question too. So I forgot that too. All right. So let's cover this question. So, all right. All right. True or false? So, yeah. Okay. All right. So let's go through it. So here's how you might justify it. So you say you take in your vector x, okay? So now take an n-dimensional vector, and the definition of being positive definite means that for any non-zero vector, you need to do x transpose times the matrix times x again. That needs to be greater than 0. It can be equal to 0 if x is a 0 vector, of course. Now, and then for this, you just literally apply the definition of what it means. So what happened is the main potentially confusing part is that you have like A transpose A, that is the matrix, not A. So we're asking for A transpose A. But when you do this, you can, like this thing here simplifies to this, which is like a vector with a vector. So it's like a vector dot product with another vector, which is AX, right? And AX is a valid matrix vector because you have A as an X, so it's an M by N matrix times an N by 1 matrix, which is a vector, then you get an M by N, M by 1 vector. And whenever you see something like this, like something transpose with itself, then that turns in that's the same thing mathematically as this term, which is something squared, so it's greater than or equal to 0, so it's at least positive semi-definite. Now, to show that it's positive definite, you would have to argue that the only time this is 0 is when x is a 0 vector, or if the null space of A is just a 0 vector. But we know from the definition that if A is a full rank matrix, then that's basically the case. So it's a positive definite. So this is basically from like lecture 2, the linear algebra review, and then part of the reason why we cover linear algebra so much is that it happens basically in like every lecture. We talked about things like like Kalman filtering, where we had these huge matrices, and then we had to think about how do they work and so on. All right, so moving on to the next question. All right, so this is another sort of math, probability math question. So this would be more like related to lecture 3. Now, the exam is not entirely about linear algebra and probability. There's of course like robotic stuff to it, but these are just some examples of like the kind of thing we might ask from like lecture 2 and 3, basically. All right, so I'll let you think about this for a bit. So just as a hint, if you remember in lecture 3, I think I showed some plots of like the multivariate Gaussian in 2D. That's basically like what we have here, 2D Gaussian. So I showed, you know, so we showed some plot that show the probability density function, and then if you take a slice at a given, if you take like a slice of it, then that's like your isocontour at the origin, basically. So you take like the flat plane and then you can plot different, like starting from that, you can take different planes and then get like shapes of the isocontour. Oh. I'll wait until, yeah. All right, so a couple more minutes. By the way, I only have six review questions here, so like it there's more, again, there's more like, you know, linear algebra and probability here, relatively speaking, than there will be on the test, but these are just some basic concepts to, you know, that could be helpful when you think about like probabilities and stuff like that. So, and this question, I feel like the way to answer this is to know like exactly how to compute the isocontours, but if you forgot how to do that, you can also use some intuition and think about like, if you think of the shape of the isocontour, then do you think that it's not like oriented in a certain like direction? Like, because I had something similar to this before. Like I was taking some exam and I forgot like what the exact formula was, but I just remembered I thought more about what the isocontours might look like just from remembering, you know, the diagram that I just showed, and then that kind of helped me. Anyway, maybe we should get into the solution here. So, all right. So here's what we have. So mathematically, the direction of the major axis of the isocontour will be given by the eigenvector that corresponds to the largest eigenvalue of the covariance matrix. So if you recall from, I think we had a question like that in homework 1, where you had to compute some eigenvalues. So if you want to do that, you can just, like we covered this formula, like it's the determinant of like lambda times the identity minus the matrix. You set it equal to 0, and then you solve for lambda. Now here you do have to use the quadratic formula to figure out what the lambda values are. But when you do that, it turns out to simplify into some nice numbers. So you get either lambda equal 1 or 3. Yeah. And then basically I feel like the easiest way is just to go back to the equation of, what does it mean to be an eigenvalue or an eigenvector? That means you have a times x equals lambda times x. So I just put that in here, and then if you could just plug in the different values into this equation, and then this one is the one that works out. So yeah, then this is just like how you would compute it, mathematically. I mean, I guess another way to think about it is, well, if you have like positive numbers in the diagonal, they're like positively correlated. So we think, maybe the isocontours are shaped in a way that, if the first component is positive, it's more likely the second one is positive. And so that might eliminate something like, well, maybe the first answer, since they have like a negative correlation between the two components. So yeah.
I don't remember about isocontours or mathematical stuff like this. So will we provide any hints about the concept like this during the exam?
Well, all right, so you're asking, will you get some hints about the concept? Well, there are a handful of questions where I said, here's a hint. Yeah, there's a handful of those questions, I think. But if you remember, we talked a little bit about this in lecture 3. So we talked in my opinion, this is sort of like a hybrid between part of lecture 3 and then the homework question where we talked about the eigenvalue. So there's like a hybrid between the two. So it's meant to stretch your comfort zone a little bit. Yeah.
I mean, maybe the most difficult part for this question is to know how to calculate the direction of the major axis of Gaussian. That's so complex, right? So if we don't even know what this means, how can we just figure this out?
Well, yeah, you kind of have to know what the concept mean to answer. Yeah. Yeah. Question? All right, so you're asking, yeah, if you forgot the exact formula, but you write out like your intuition and how many points you might get. Well, yeah, we will give partial credit. It depends on how accurate your intuition is. So, something that basically describes this might only lose 1 point out of 4, but something that's completely off, there's limit to how much we can give. I think the important thing is we have to be consistent in how we grade things. Because if there's one thing that, there's the 2 things that students don't like, if they got graded more harshly than other students. And also if the material is very different from what we covered in class. So, yeah.
So after this question, I'm curious about if we just circle one choice randomly, we don't know what to do. We got some prediction points.
If you circle the right answer, but you don't justify,
Yeah.
let me discuss it let me think about it. Well, let's move on to the next question. So I feel like this one I feel like is more relevant to what we covered in class, right? We directly covered an example of find the maximum value of this subject to a constraint. Do you remember this question that we covered in class? All right, then let's try this one. Yeah, and by the way, when you do these questions on the midterm, I said, you can leave your answer, your final answer, like a fraction if you want. So if there's like something that doesn't cleanly reduce to an integer, you can always just leave it as a fraction, then it's not a big deal. Right, how are we doing? Hopefully you've at least written out the Lagrangian. Yeah. Okay, we directly covered it in the mathematical programming lecture. Like it's basically like the same thing, just write out the Lagrangian, you take the gradient, set it equal to 0, then you do some other stuff. Maybe let's go through the answer because I want to make sure we get to all the questions. So, all right. So here is roughly the step. Now, if you got like basically everything, but you just have like a minor, math error at the end, like you might get everything but 1 point. Right. So it depends on how much you got these steps. So whenever you see the equation of like, find the maximum value of this subject to some constraint, then you should immediately be thinking about, you form the Lagrangian f of x, y, and lambda, which is capital F here, is equal to this part from f, and then this part from g. So whenever you have g, just make sure that you move the, the 136 to the other side because you want to make it equal to 0. And that's how we standardize everything. And then you take the gradient, and then you set it equal to 0. So the gradient, you take the derivative with respect to x for the first component. So you get 5, the x goes away, and then you get 2 lambda x. Yeah. Same thing for the second component, and then the third one, the f part goes away, then you get the lambda goes away, then you get whatever we're left with g. And then at this point, it becomes an exercise in, solving a system of equations. So because there's only 3 variables, hopefully it's not too much work. So if you just do something like, x equals 5 over 2 lambda, and when you just do something like this, and then you get, yeah, then you get the second equation here. And yeah, I guess basically when you do the algebra, you'll get something like this. So yeah. Or maybe the x should be maybe there should be a negative here. Yeah, I'll double check this. I'll do this. Yeah. 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 I think so. I think these are I think these are correct. I think you just have to maybe like I think you have to move. I think there should be a negative by the x and then a positive by the y. So yeah, I'll just double check that and then make sure it's all good. Yeah. So again, this is basically how you would mechanically do this kind of stuff. Yeah. All right, so maybe we should cover the next question quickly. So it's on Bayesian networks. So I think some of you asked me about more practice questions about like if you have a Bayesian net that looks like this, what are the independence assumptions that are guaranteed to be true? All right, so here's your example. All right, is A guaranteed to be independent of B? Yes or no? Nope. It's not guaranteed to be independent because you have an active path between A and B. What about A and D? So you have A and D. If you condition on B and H, so A is conditionally independent of D given B and H. Is it guaranteed to be true? Is it guaranteed to be independent or not? They're true or false? Yeah, so it's false. So, but why is that the case? So all right, if this is false, that means there has to be an active path between them. Does everyone see why? Because, all right, if you condition on B, you block the path to here. So there's no path. But what about conditioning on H? Then there's an active path from A to D. Because it goes here, then here, then back, then here. Because F and D are a B, they form a B intersection, and then H is like the successor to that. And then we covered in class that you have a B successor, there's an active path if the bottom part is observed, or if one of its descendants is observed. And so there's an active path from A to B, and then B is false. All right, A is conditionally independent of E given F. True or false? True or false? All right, it's true. So why is that? Because when you condition on F, you're observing this. So let's look at all the active paths between A and E, right? So you have A and E. All right. So A can try going from B to E, but this is a B intersection. Like it's a little bit tricky because the arrows are pointing up, whereas in the slide, we should usually show them pointing downward. But just remember that whenever you have arrows pointing to the same thing, if it's not observed, it blocks the path. So A does not have a path to E here, to E there. Now, if F is observed, A can try to go from here to here, but F blocks the path because it's just a serial chain. And so both paths to E, but and then there's also like, it can try going from A to B to D to G to H, but H is not observed, so it also blocks the path. Hi, G is conditionally independent of E given B. Yep, true or false? All right, it's false. Why is that? All right, you condition on B here, right? So we have G and then we have, so this is not an active path. It blocks from, G cannot go to E from here. But let's look at the other way. You can have a path from G to F to A to B and then to E, right? And then A to E is active because B is observed. And so it activates a path between A and E. And then that means A is not guaranteed to be independent of E. And then therefore it will propagate through the serial chain to G. So, and again, remember that the other tricky part is that when you're looking at active path, you also have to look at, you have to find different undirected paths, basically. But you use rules from the arrow to indicate whether if something is observed or not, then you can either have an active path or not between them. And then F is conditionally independent of C given D. True or false? False. Why is that? You condition on D, right? And then you have F, and then C. So F, there's a path from F to A to B, and then to C. Now, this is not observed. It's a B structure, like A and C go to B, but because B is observed, that is a descendant of the B structure, so it activates the influence from A to B to D to B to C. And so they are not guaranteed to be independent. Last one, E is conditionally independent of D given B. All right, I'm just gonna move on quickly, but I want to make sure we get to the last two questions as well. So I know this is going a bit quickly, so you can always think more about it in your own time too. All right, true. Why do you think? So you had B, so E, like E can try to go from B to D, but that's a serial chain, so it just blocks. Now, E can try to go here, but H is not observed, so it blocks the path to them. Same thing when you try to go from A to D. So it's a serial chain, so it blocks the path. So yeah, hopefully that's a helpful example. If you're a little bit confused about that, I would recommend just looking back at the video recording. I'll try to post it by tonight, and then you'll get to see it. All right, so configuration spaces. So when you look at this structure, the question that we then ask is, what are the degrees of freedom of this planar mechanism with two overlapping joints? Which means that's this thing over here. So the circle here is interpreted as two revolute joints that overlap each other. So every joint really connects two links, but you have two revolute joints here. And then this thing here, the one that looks like this, interpret that as a prismatic joint connecting two links. Yeah. So if you remember what we covered in class about Grubler's formula, so yeah. I mean, I think the biggest challenge here is like thinking about what are the links here, then what are the joints? And sometimes the visuals make it a little bit more complicated than it seems. So I'll try to make sure that visually it's a bit clear. Like whenever you see this, always think of this thing as ground, and there's one ground. So in Grubler's formula, you have the number of links, which includes ground, but there's only one ground. So don't think that you have multiple grounds. Here, it's one ground. This is a revolute joint, so revolute, 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 revolute. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9 joints. So we have 9 joints here. So yeah, that's why you have 9 joints here. It's 8 revolute plus 1 prismatic. And then there's 8 links. So you have 1 link there, a second link, the third link, the fourth link, the fifth link. Now this is 6 and 7 here. Then there's ground, so that's 8. And then you get 3, 8 minus 1 minus 9 plus, and remember that this thing is always 1 if you have revolute or prismatic, like the F here. And then you get basically get 3. So right. Yeah, so hopefully that's somewhat clear. Yeah, and again, whenever you see Grubler's formula, like this M here is going to be 3 or 6, right? If it's planar, it's 3. So if you see this, just think of M equals 3, basically. All right, sorry, last question for now, and I'm sorry, we only have a few minutes left, but I can stick around for a few more minutes if you want to. Assuming no one kicks me out here. So if you have the extended comment filter, I think there are a lot of questions on the homework when you were working on this. So like, if you think of the following scalar system with the state and the observation, then you might ask you write the equation for the extended comment filter, and there's 4 parts to it. So you have the lowercase g, that is the nonlinear state transition. You have capital G, that's the Jacobian. And then you have lowercase h and uppercase h for the observation. And basically, if you're given this, we would just tell you, you have an unknown constant alpha that you're also trying to estimate. And even though like it's constant in the dynamics, you might still include it in your state vector. And then so the question is like, what are your what are these four components, right? So the way that I chose to do this is, what I did is, you define the augmented state vector as this thing, so you have, yeah. Theta transpose. So, this is our like state, it's two-dimensional. Now, note here that there's also no control. So maybe I should have said this explicitly, but there's no control here, like there's no u. So normally the function g has a u and a mu if you look at the textbook. But to make it simpler, we have no like robot controlling. So just like a state estimation without a robot control. And I think if you also notice what the book does is they do things like g of u and mu plus the noise term. So I chose to pull the noise term out here. And then this g is like the deterministic part, and then there's extra noise. But to me, it doesn't matter if you include that noise term in there or not, because when you take the Jacobian, the noise term goes away anyway. And then this is just straight from the formula of how do you do the Jacobian. So it's partial derivative of this thing, and then I put in 0 and 1 because it's just going to turn into 0 or 1. Yeah, and then it's also the same thing here. So for H, I also didn't include the noise term. So again, like I personally, I feel like in my opinion, it's a design choice if you want to include the noise term like omega and b in your G function and your H function or not. Like I chose not to include it, but either way, it shouldn't matter when you compute the Jacobian because the terms go away anyway. And I think this is similar to what you had in homework 2, question 3. I think we had a lot of questions about that. So this is like an example of how you would do it for a similar problem. Anyway, so I'm over by a minute, but if you have any questions, you can just ask me now or yeah. Actually, I do have office hours, starting now. So yeah, any last minute question about this question about this? Right, so I'll see you Wednesday. Yeah. And by the way, I know that I mean it's easy for me to say, but I do recognize that the exam can be a little bit stressful, but I don't really have any intentions of being super strict. Like you don't need to get every question right to pass or whatever. So it's not. I'm gonna try to be reasonable with it. So yeah. All right. Thank you very much, and we'll see you Wednesday or in office hours if you want to chat.